We are starting a 6-day series on 5G and beyond. And each day you will have different flavors, starting from semiconductor to broadcasting to blockchain and many others, as you have seen. And today it's our pleasure to have Mr. Anindya Saha. He has a BTech from IIT Varanasi, ME from IAC. He has been working with Semiconductor Complex Limited, Texas Instruments, Broadcom, and many others with a lot of semiconductor background, but also currently he's CTO of Sankhya Labs. And he's an expert in also in software-defined radio architecture design and implementation. So today our topic is an introduction to ATSC 3.0. There is a lot more that can be detailed out, but for the community, we wanted to have as an introduction session. This is a next generation broadcast standard, and many people say, you know, against the 5G, is it a complementary technology? Is it something competing? So today, let's hear from Anindya on ATSC 3.0. So with that note, I welcome Anindya. Let's give a round of applause and let's start that presentation. Thank you, Anindya. Handing over to you.
Thank you, sir. Welcome, everyone. Actually, it has rained a little bit in Bangalore, so the weather is pretty cool. I believe people can brace for a little bit long session. This is a very interesting topic, and so let's get started. So, okay, so going to the agenda, we'll start with an overview of what this standard is all about, ATSC 3.0. And the next section, we will basically dive a little bit in details into the physical layer and the transport layer aspects. This is where, you know, the meat of the standard is in terms of determining the quality and capacity abilities. And, you know, then we'll look at the broadcast aspects of supporting video, audio, emergency alerting, as well as the security aspects. Then, since we are on the theme of 5G, you know, we will examine certain aspects of where this standard has synergies with 5G. We'll look at a few deployments that have been done and they are kind of still starting up. And then we'll look and then we'll conclude with the promise of ATSC 3, what it promises, just a short summary. So let's go to the next slide. Let's look at what the goals were. So obviously, when ATSC 3.0 started, you know, this ATSC 3, first of all, let me clarify, it stands for Advanced Television Standards Committee. And yeah, this is basically a consists of participation about, I would say, 150 international countries, 50 countries, and you know, about 400 people have kind of contributed towards the development of this standard. And this was predated by the standard called ATSC 1.0 and 2.0, which had their own inefficiencies. So when the standard committee met, they basically, the top thing on their mind was that, you know, they are going to create something which is not backward compatible. You know, and that's a very big thing. I mean, if people who know the standards body know that. So it was like similar to a transition, just like the analog to the digital transition in the broadcasting world. And the topmost thing which was there in the mind of the creators was that there needs to be, it needs to be so good and so improved compared to the previous standards that it justifies the return on investment. And at the time when this was being defined, it was not mandated by the FCC and the regulatory bodies that this people will ask, the regulatory body will ask them to change over. So inherently, there was a desire that this standard needs to be extremely good. So that is where it kind of originated from. And looking at the new emerging business models of the broadcasters, it was thought that one of the prime things or the most important things is that how to reach to more viewers on more devices. And the second important thing is that the consumer behavior has also been changing a lot compared to what it was, several years ago. Several years ago, people used to watch content which was basically classified as linear TV. You will get you have time slots at which programs will occur, and then the whole family will sit in front of the television and watch. But now all the consumer habits and the viewing habits have completely changed. People are watching whatever they want, whenever they want, and at any different place. The place is not a constraint. So the behavior of the consumers has significantly changed. And then how should a broadcasting standard keep up with that? That was one of the challenges. Of course, the other inherent challenge was how to provide higher quality, better quality of audio and video, and of course, provide more accessibility. So these were some of the top level goals with which the standards committee or the standards body started. So let us see what the key goals, or I would say the key advancements, which, because now the standard is already there, what are things which people really people have accomplished in this. Then we'll dive into the details. So the first thing is additional capacity, and we will know. So basically, that means more channels, more pixels, and we'll kind of touch upon this in detail when we go to the physical layer section. Better reception. It is not only terrestrial reception, but you should have reception which is pervasive. You should have it indoor, you should have it in vehicles, and it should be available on mobile devices. Hybrid OTT and OTA. So what this means is that your transport layer of the broadcasting needs to be all IP based, so that it can easily go between broadcast and broadband, and it can embrace both. Enhanced consumer experience. So this means that improved video and audio quality, better accessibility, more interactivity, ability of giving emergency alerts, which was not so much available in the previous generation standards, and capability to spawn off new business models. And the reason why this is very important is because whenever a standard is created, it is always, the proliferation of the standard is always driven by what kind of businesses get attracted or get created by that. So, advanced kinds of advertising like, dynamic or local ad insertion, and then pay-per-view and subscription services. How can the content be encrypted to enable these? And then advanced methods of service usage reporting. And finally, the most important one is data casting. So if you look at data casting, you can consider broadcast as a general data delivery thing. Video is just one form of data, and then there could be other forms of data. One can think of firmware updates for IoT or even for automobiles. All of those can be looked as can be addressed by broadcast. So these are some of the key advancements which the standard enables. Now let me go to the next slide, which is on the physical layer. And this is a little bit of a detailed slide, and it basically shows that the physical layer architecture shows it's a little bit of a beast, because it's quite complicated. It involves a lot of communication, signal processing aspects which have gone into the waveform design. So broadly, you can see there are 4 sections. There is an input formatting section. There is a bit interleaving, coding and modulation section, framing and interleaving section, and the waveform generation. So one of the important things which I should tell before we start is that this standard is also OFDM based. And I'm just flashing the kind of OFDM 50 sizes that are there. And let's okay. Let me show the cursor around so that you can see. So let me walk through some of the functionality of these different blocks. So at the input, you have different. You have what is called as the studio link from which the video is coming, and it is supposed to go to provide different services. So it goes to an encapsulation module, which basically combines multiple input streams with frames. And then there is a scheduler which basically puts them in order, in the desired order, and then it is packetized. Once it is packetized, it goes through the scrambling block, which basically scrambles the data. And then out of this input formatter, you get what is called as multiple physical layer pipes. And just remember this word called PLP, because we'll again refer to this in the next slide. And what goes as an input to the next module, which is the BICM module, is multiple PLPs. And inside the BICM module, you have the forward error correction block, which basically adds redundancy information for data protection. For each of these physical layer pipes, you have a bit-interleaver, which randomizes the data bit placement within the pipe to reduce the impact of the channel. And then you have a modulation mapper. So the job of the modulation mapper, just like any other OFDM waveform which you will be knowing, is to assign a group of bits to a symbol, within a pipe. So this is one of the key important pieces with the BICM, and we will kind of compare this with the other standards in some of the later on slides. So how and that kind of determines how good the spectral efficiency of this waveform is. Next, we go to the framing and interleaving block. Now you can see three components here. The first component is time interleaving. Now, one of the important things which we need to realize in the broadcast world is that the frame durations are kind of long. They're like the minimum frame duration in ATSC3 is 50 milliseconds, and then you can increment every 5 milliseconds. Now, when the frame durations are long, you have an ability to randomize, the incoming bits or the incoming modulated symbols in time domain and do some kind of interleaving. And what this enables you is to create an additional time diversity, when the waveform goes from the transmitter to the receiver. This is followed by an OFDM framing module. There is some amount of multiplexing here, and then followed by a frequency interleaving. So frequency interleaving is again a very important aspect because, in a real world, there are channel effects like deep fades or nulls, which needs to be countered. And broadcast is another medium. If you really think about it, there is no return path, unlike a typical cellular standard where you have a downlink and an uplink. So really, if you lose the packet, you don't see the video. So it is very important that both these aspects, time interleaving and frequency interleaving, are added so that the waveform which goes out of the transmitter is really, really robust. So in some sense, at a very coarse level, you can think that you kind of randomize the packets in time and randomize the packets in the frequency domain because it's FDM to counter, not only give a good time diversity, but also to give a good amount of frequency diversity. Now we come to the last block, which is the waveform generation block. And here you can see that we have the usual, things. There is the pilot insertion block. Now the pilot insertion part, as we all know in OFDM, you basically reserve some tones for channel estimation, synchronization, also a little bit of PAPR reduction. And then you have the IF50 or the inverse fast Fourier transform block, which basically generates your OFDM waveform, and then followed by the guard interval addition or insertion. And then finally you add another segment at the beginning of the waveform, which we call as the bootstrap. In addition to the bootstrap, we also add what is the preamble, and basically the bootstrap and the preamble perform some more tasks, which is basically used for detection and frame synchronization and some additional signal. So this is basically an overview of the physical layer architecture. Let's keep in mind these four blocks: the formatter, the BICM, the framing and interleaving, and finally the waveform generator. And let's go to the next Okay, so before I move to the next slide, one thing which I wanted to show is the fact that if you look at the kind of FFTs, you go from all the way from 8K to 32K. So this basically means, you know, a really, really high capacity channel. You know, 32K FFT means the amount of carriers are really huge. You can see useful carriers roughly close to 28K. So within a bandwidth of 6 megahertz, you know, we are able to achieve a lot of, you know, very high spectral efficiency, and that is what we will see in the next slide. So you can interlink this with the previous slide, and what we are showing here is basically the BICM or the bit interleave, the performance of the BICM module. Now, on the x-axis, we are actually showing the SNR, and on the y-axis, we are showing, you can call it as the spectral link efficiency. And if you look at this blue line, the blue line actually shows the theoretical limit of, you know, how many bits per second per hertz we can push through the air for a given SNR. And if you look at this, you know, at one end we have a very low capacity, and this is very robust kind of possibilities here. Especially, you know, you can see lower spectral efficiency and lower SNR, and so some of these are very robust. And then at the higher end, as you go to the higher end, you have very high capacity modulation mod cards, modulation and coding rate combinations, but then they are less robust. So if you think about it, this standard basically enables you, gives you the flexibility to go towards from low capacity, robust modulation coding methods towards high capacity, less robust methods. And you know, if you look at this, one of the things which you will notice is an important thing which is called as A53. And what was A53? So A-53 is actually what was called as ATSC 1.0, and the capacity there, the SNR there used to be somewhere close to 15.5 dB. And the disadvantage was that it was just a point. You know, it didn't have flexibility in terms of going to lower mod cards or higher mod cards to trade off the spectral efficiency and the SNR. So this was one of the important things. The other important thing was ATSC 1.0 was about you know, people wanted a very significant improvement. So one of the goals which the ATSC standard committee set is that they need to get at least a 30% higher efficiency compared to what the ATSC 1 used to give. So that was one of the metrics which was kept in mind while coming up with this. So if you see roughly, you can see that there's a roughly, I mean, at the same SNR, there is a 30% jump in the spectral efficiency. Now let's look at some of these red dots here. If you look at this, one of the things which you will notice is that it is quite close to the channel limit. It doesn't overlap, but it is quite close, which means that a lot of work has gone in to define the waveform to make sure it is close to the channel capacity, definitely better than the previous ones. You can see some of the green lines also. So this is a competing broadcast standard, T2, which originated in Europe. It is kind of close, but then at most of the places, I would say ATSC3 kind of beats it, at least by 1 dB in most of the places. And if you look at these red dots, the other important thing which comes to my mind is the fact that now the broadcaster has so many choices. You know, he can choose to deliver a service which is of low capacity and very, very robust. And at the same time, he can also choose to deliver a service which needs really high capacity. And if you look at this point, you can see that it can go all the way up to 256 QAM, 1K QAM, and even 4K QAM. So that is how this standard has been defined. Now, interestingly, you can think of how do you make use of it. So consider one of the use cases of this of ATSC 3.0, which is that let's say you want to watch a 4K kind of content, an ultra HD sports or drama. Then you might like to target something like a rooftop antenna, you know, where you really want very, very high capacity. The goal there is to get more bits per second. You can see you can get close to 10 or 8. Okay, and you are less worried about the robustness. So what happens with a rooftop antenna is that you get a lot of link margin, and that enables you to achieve these kind of high SNRs. Now, as a broadcaster who wants to make money, he might actually like that in the same RF band. How about the possibility of providing both kind of services? A low capacity robust service as well as a high capacity and maybe less robust service. Can he combine this together? So the standard actually gives the ability to combine this by providing what is called as physical layer pipe or PLP. We kind of briefly touched upon that in the previous section when we looked at the chain, but we'll go to that a little bit in detail later on. So essentially, what this shows as a summary is that yes, ATSC 3.0 gives a lot of flavors of modulation and coding rates, which the previous generation did not give, and tries to achieve as much closer to the Shannon limit in terms of the capacity for a given SNR. So let us look at the framing hierarchy of the standard. So essentially, if you look at the frame hierarchy, you have what are called as the frames, which is the largest physical layer container to carry the data. You have subframes, which is basically within a frame. Each frame has one or more subframes, and then subframes could be of multiple types. And the lowest granularity level is what is called as physical layer pipes, or what we call as PLP. And what is possible here to do is that each subframe can have multiple PLPs, and multiple PLPs could be present. It could allow multiple services to coexist. And really, a PLP's capacity is determined by the modulation order and the number of cells allocated, and the FEC kind of rates. Now, in general, what has been allocated by the standard is a maximum of 4 PLPs for a given service. And of course, you can have about maximum of 64 distinct PLPs in an RF channel. That is what the standard allows. So moving on, let us look at how signaling happens in this standard. So one of the key things in this standard is if you look at the frame structure, one of the things you will see that it consists of, this is the sequence. It first starts with a bootstrap signal, followed by a preamble, and then followed by the payload or the data frame. Now, the bootstrap design is quite unique, and it deserves a lot of attention. One of the things you will notice is that it occupies lesser bandwidth. So if the whole bandwidth here is 6 megahertz, the bootstrap occupies only 5 megahertz. And what is the function of bootstrap? So the most important function of the bootstrap, for the receiver, is that it allows us to synchronize and lock into the signal. And the bootstrap contains a lot of other attributes. I'm just showing that in the call out. It has various bits which enable you to mention about the kind of services it contains. It allows you to discover or do things like timing synchronization, frequency acquisition. And one of the important things of bootstrap is that it serves like an entry point to a waveform. And let's just think about it a little bit. So for example, if you have a receiver which is receiving this waveform, it will first decode the bootstrap. And it will look at the service template of that and figure out whether it should go ahead and decode the remainder of the preamble and the data payload, or it should skip that. Now the bootstrap signal, that's why that gives you the flexibility to do that by decoding the parameters which are present. And that is why it is also called as the entry point. One of the important things why the signal design has been done with a bootstrap in mind is that, let's say tomorrow somebody wants to enhance some ability of the waveform, for example, a different video codec or a different modulation scheme or something. In which case, what can happen is that he can simply change the version number in the bootstrap and still allow the legacy receivers to work. And now why was it thought like that? That you need to allow legacy receivers to work. And if you think about it, what can happen is that if I update any attribute of the waveform, it is possible that the existing receivers which are there in the ecosystem might suddenly stop working. Now, what was achieved with the bootstrap was that a receiver, if it finds that, once by decoding the bootstrap, if it finds that the version of the waveform which is following the bootstrap is not something which it can handle or which can demodulate, then it will simply skip. So bootstrap was a very, I would say a very novel way to make sure that while you keep updating your waveform towards more advanced types, your receivers don't need to change. The old receivers can still continue working with, let's say right now, the 3.0 version. And let's say in future, we come up with versions like 3.1, 3.2. The receivers need not be changed. But yeah, more advanced receivers can come and they can probably decode, do a better job. But then the existing receivers need not be replaced. So that was the thought process. And that's why Bootstrap is called as a universal entry point to the waveform. The other important thing about Bootstrap, which I wanted to mention, is that it is very robust. It works pretty much below the noise floor, 6 dB below the noise floor with a frame rate of 0.01. That means that even if the signal is buried under noise, a receiver can demodulate it. So that really talks about the robustness of the signal. Usually it consists of 4 to 5 symbols. Okay, so following the bootstrap, you have what is called as the L1 basic and L1 detail. So L1 basic basically has parameters which enable decoding things about L1 detail. And then subsequently, once the L1 detail is decoded, it enables you to get all the parameters, subsequent parameters regarding the OFDM configuration of the subframes and the payloads. So one of the important things I wanted to mention here is about the kind of attributes which are signaled in this in the bootstrap, which is basically one is the sampling frequency, the channel bandwidth, kind of preamble selection you have to do, and also time to next similar frame. So basically, you can think of this kind of structure of bootstrap, preamble, and frames following one another, and then the bootstrap will tell when is the next frame going to come. And basically, if a receiver can kind of decide, if a receiver finds that yes, this bootstrap is not for me, or this waveform is not for me, it can sample the bootstrap again, after some interval of time by looking at this field, which is called time to next frame. So in a nutshell, Bootstrap is a very, very key component, and this is one of the things which also enables extensibility of the waveform, which other waveforms or previous broadcasting standards did not provide. So let's go to one of the very interesting features of this standard, which is called the layer division multiplexing, and let's take a little bit time to understand what it is. Now, layer division multiplexing is based really upon the superposition of two signals of different amplitude levels, and I have tried to show that here in the right-hand side. You can see, two layers. One is called the enhanced layer, and then there is another layer called the core layer, which is kind of riding on top of it. And then it is extensible. You can come up with, so right now, let's say ATSC 3.0 defines only 2 layers, but it's possible in the future that with better signal processing techniques, you might be able to come up with more layers. Now, so you can see two terms here. One is called the core layer and one is called the enhanced layer. And so what is core layer and what is enhanced layer? So when a broadcaster is transmitting, what he ensures is that he utilizes the same bandwidth and he's superimposing the two signals one on top of another. And this is what is called as power combining or amplitude superposition. So let's have a look at how this happens. So if you recall, this looks similar to the previous chain that we saw, but then you have just two parts here. One is called the core layer and one is the enhanced layer. So you can see core PLP and enhanced PLP. And there is an injection level with which you can control how much of the core layer versus enhanced layer, what is the power combining ratio that should go in the final combined PLP. And what this allows broadcasters to do is to, they can use different kind of services on the core layer and the enhanced layers. They can use different mod codes and also different FEC attributes, code rate attributes. Now, once a receive, so when this is transmitted, how does a receiver receive? So a receiver which is LDM capable, obviously, first it has to decide whether it wants the core layer or the enhanced layer or whether it wants both. So if you look at this spectrum, you see that the core layer is riding on the top and the enhanced layer is below it. So obviously, one of the things which comes straight away is the fact that the signal to noise ratio of the core layer is far, far more superior than the enhanced layer. So what I'm showing here is basically a receiver where first the receiver will decode the core layer. This is what is shown as the decoded core PLP. And then it will re-encode it and subtract it from the input combined PLP to generate what is called as the enhanced PLP, or you can also call it the bottom layer. And then this enhanced PLP will be further decoded to get the enhanced layer. So this is the mechanism which a receiver, an LDM capable receiver, has to follow to make sure it receives either the decoded enhanced PLP or maybe the core layer PLP also. If it wants both, it has to do both the operations. So obviously there is a sequential aspect. You have to decode the core layer PLP first and the enhanced PLP later. And one of the things which of course is mentioned here, and I will go to that, I'll explain that a little bit, is the fact that because the core layer PLP or the core layer has a higher signal strength, obviously, if you look at from a transmitter point of view, that is going to have far more reach than the enhanced layer. And you can think of this as somewhat like a double-decker bus, where you have the lower story is the enhanced layer and the upper story includes the core layer, and you're delivering more passengers, which means higher service throughput, but within the same footprint or the same spectrum. And that is why it provides a large gain in transmission efficiency. Now, while LDM does that, one of the important things to note also is the thought process which went behind this. The important thought process here, if you remember, when we looked at one of the key features, was the ability to serve both fixed receivers as well as mobile receivers. And this is exactly what it does. The core layer, if you think about it, has much higher signal to noise ratio. So that's why it has a much wider reach, and it can go for long range. And definitely, if you consider mobile receivers which have negative antenna gain, they would need a much more stronger signal to demodulate. So typically, if you think about it, the core layer is meant typically for the mobile receivers or the mobile broadcast receivers. Whereas if you consider the enhanced layers, they can easily be addressed or they can easily be received by receivers which have something like a rooftop antenna, about 9 or 6 dBi gain, which gives a very good link budget and can decode it, can demodulate and decode it very efficiently. So what LDM does, in a sense, is that it gives the ability to the broadcaster to serve two types of customers at the same time using the same spectrum. One is the mobile customer, the other is the customer who is who is viewing the rooftop reception on a fixed TV. So that is the beauty of LDM. Other important aspect is the fact that LDM is I mean, what has been used here is one of the rudimentary forms of what is also called as a non-orthogonal multiple axis in 5G, NOMA, and one of our later lectures down this week also touches upon that. So please listen in for more details. The other important thing I wanted to also show here is the kind of constellation view that you get. You can see that the enhanced constellation or the enhanced layer constellation in this case is like 128 QAM or 256 QAM. But the LDM constellation looks like a combination of I mean, in this case, if you consider QPSK, it will look like this constellation is superimposed 4 times, along each of the 4 quadrants. So that is how an LDM constellation looks like. Now, this is one of the ways of which multiplexing is done, but then the standard does not prohibit us from using the conventional methods of multiplexing like EDM and FDM. So essentially, it gives you flexibility, a lot of flexibility to use any kind of multiplexing for providing its services. So let's go to the next slide. So here we'll talk a little bit about single frequency networks. So what are single frequency networks? So if you consider, a single stick antenna, and when I call single stick antenna, it basically means, like what we see in our Doordarshan tower. It's just like a really long vertical structure, which is radiating huge amount of power. Now, if you consider a single stick antenna, what you will encounter is that at some places, because of propagation conditions or the terrain, the signal strength is not really constant, it varies. And it will also happen because of the path loss also, which we all understand. Now, if a broadcaster wants to actually provide a very uniform coverage or wants to extend the coverage, what should he do? So one of the ways by which he can do it is what we call as SFN or single frequency network. And in that configuration, what he will do is that he will install multiple of these transmitters and make sure that they are radiating the same content and they are time synchronized. So what this allows, now if you think of it from a receiver point of view, what happens is the receiver now sees a very good SNR because he sees an addition of power from all these transmitting sources. He sees a sum total of power from all these transmitting sources, and thereby all the coverage holes which were originally present with the presence of one transmitter kind of get eliminated because all these coverage holes are addressed. And now you end up getting you can basically end up not only extending your coverage but also adding more capacity because now you are kind of raising the SNR that is being seen throughout the entire region. And because you use OFDM, the inter-site distances and all can be all addressed in terms of deployment by choosing the appropriate guard interval, so that I mean these multiple transmitters should not appear as interference free. So there are ways to handle it by choosing the appropriate guard interval. So this is one example of a single frequency network. I mean, in this case, we are showing that if you have a single network, the radio horizon will be limited. But if I want to extend it to more markets, I will install multiple of this so that I can go from one DMA to another. So DMA stands basically for market areas, designated market areas. Yes. So imagine, let's say from Bangalore, if all the way from some place in the city to the airport, if you want to view a particular channel continuously, what you ideally need is a single frequency network all the way, so that you have a continuous, high throughput capable SNR along that particular route, and which can deliver, high capacity. And this is another use case of single frequency network, where basically you can use it to expand or enhance the throughput or the coverage as well. So these are the two use cases of how an SFN would be used. Here I have showed the example of Washington DC area, and here you can see WRC TV. This is one of the broadcasting stations. On the left-hand side, there is only a single antenna, or as they call single stick. And on the right-hand side, you can see 4 additional towers, which are shown in dark red. And you can see that not only is the coverage area improved because of the SFN, but also regions where the coverage was poor earlier, there because of the additive signal power, the signal strength is high. So typically such kind of diagrams or pictures are called as heat maps, basically show the relative signal strength. Now moving on to the different scenarios. So now that we understand ATSC3 gives us all these capabilities, how do we provide these services? So this is one of the scenario, where a single transmission is done using a single antenna, and you are able to receive deep indoor reception. So you can see the kind of attributes that are there. So you can consider that the broadcaster wants to transmit one HD service and one mobile and audio signaling service. And the important thing is the choice of mod cards. You can see that both are QPSK, which means he has chosen very robust modulation methods. He has gone to a lower FFT. One of the advantages of, or I would say first, the disadvantage of a very high FFT is that because your carrier spacing is so small, your receivers are very, very sensitive to phase noise. So sometimes when you want a very, very robust reception, you might like to choose a FFT which is smaller, where the reception, where the reception will be far more robust. And then there is a choice of the kind of mod cords of the NTPC and the choice of the guard interval and kind of the framing frame timings. So you can see that this kind of service is basically, it's customized for not only portable receivers, but also for indoor reception. You can see that the broadcaster has kind of partitioned the PLPs in terms of the capacity. The audio service is taking about a kind of high capacity. It's an HD audio, and mobile is basically taking very low capacity. And you can also see the corresponding DSNR, is the PLP2 actually is kind of works at negative SNR, whereas the first service, the HD audio service, needs positive +2 dB SNR. You can also see the robustness to the Doppler, which means that if these receivers were to be mobile, then the PLP2 is definitely far more robust to mobility. It has ability to withstand something like 180, close to 180 miles per hour, whereas the HD audio service can go somewhere close to 90. So this is one example of how, in this case, we say 2 PLPs could be parts of the same subframe and be delivered by the broadcaster for 2 different services. Okay, so in this example, this is a different example, and here the broadcaster wants to deliver 3 services. You can see the kind of services. There is a fixed service, which is meant for fixed terrestrial receiver, and then there is a robust service, which is obviously targeted either towards deep indoor, or it is targeted towards a mobile. It could be any of these. And you can see how the 3 PLPs are. Essentially, you can see in terms of the capacity, the fixed terrestrial one, because it has it uses the rooftop antenna reception, and it can basically needs a high SNR. We basically, because we want to push a 64 QAM kind of signal, it needs a high SNR. And then the robust services and the audio channel usually are using the lower modulation rates, lower mod cards, as well as different kind of code rates. So in this case, you can see how the relative PLP occupancy is. You can see that this is very low bit rate, 0.66, then 2.9 Mbps and roughly 9 Mbps. And so this is again, one of the ways in which a broadcaster would combine services. In this case, the example of 3 PLPs to deliver a different kind of service. So an important thing to keep in mind is that, all these services, all these PLPs are time division multiplex within the subframe, and they are being delivered kind of concurrently. So and because of the different SNRs, you can imagine that they will have different kinds of reach as well. So essentially, the kind of framing structure that ATSC has allows you to offer multiple services at the same time from the same transmitter. So that is one of the beauties of this new method. Now let's come a little bit towards mobility. And when we talk of mobility, one of the important things to understand is how capable is this in terms of offering mobility. So this was basically, a showcase which was done during the Winter Olympic Games in Korea. You can see the year 2018, and basically there was a bus in which was basically going around the stadium, and you can see that there are television panels, and then there are tablets and all which are kept, different various kind of screens, and there was basically a transmission which was going on from a single stick, which was broadcasting the Olympics. And what it was showing was that even when this was mobile, the ATSC 3.0 the reception was pretty good, and followed later with an NAB. NAB also, a similar kind of demo was held where there was an autonomous vehicle which would go around a particular, around a transmitter antenna, which was put somewhere on the hills, and the reception was pretty robust. So basically, these two demonstrations were basically to show the mobility, how capable ATSC 2.0 is in terms of the mobility aspects. So having covered this to a great detail, we can now shift gears and come to what is called as the transport layer. Now, if you look at the transport layer, what are the things that you see here? You can see on the right-hand side, this is called broadband. You can see this is the broadband protocol stack. On the left-hand side, you can see the broadcast protocol stack. So from day one, the intention was that it has to cater to a hybrid system. And if you look at the application layer protocols, you can see that on the broadcast side, you have MMTP and route. And route uses basically the dash protocol, which is similar to what HTTP uses. So basically, here itself you can see that by the choice of route and dash at the top layer, we are basically making sure that a particular content can be received via broadband as well as broadcast. Now, MMTP is basically multimedia transport. It basically supports both download, progressive download, and streaming applications. So at the top layer, you can see a player, the MPU player, which basically can aggregate the segments and play it out. Now, the most important thing, so in addition to that, you can also see the signaling layers, service announcement layers, which are usually required for setting up this any kind of service. But the most important, so that's one of the important things. And of course, the most important thing here is the fact that it all sits on, both the layers, actually both the sides, both broadband and broadcast, both of them sit on what is called as the IP layer, or they use IP as the transport. And the reason why this was done is to make sure that the receivers in future, which definitely will be broadband enabled, can be an enabler or can receive hybrid services, both via OTT as well as OTA. And this is one of the very fundamental shift which was made, in ATSC3 compared to DVB-T and other standards, which earlier used to use MPEG-2 as the transport stream. And in some sense, this gives a natural convergence. And if you really think about it in terms of hybrid services, if you say, one can think that, let's say, a broadcaster wants to transmit his main video and audio over IP. Then, additionally, what he can do is he can use his broadband channel to send alternate language tracks and things like that, and the receiver will be intelligent to stitch them together. So that is really the beauty of a converged transport layer, which is kind of IP, and that is why ATSC 3.0 is also kind of thought of as really something which is very close to something which will interwork very well with broadband standards. So let's go to some of the other aspects of ATSC 3.0. So one of the important things is it supports up to a resolution of 4K. That is what 3840 into 2160 is. Well, the standard is still extensible to support 8K as well, but those are mainly market-driven things. It supports spatial scalability for spatial resolution, and this is where SHVC comes in the picture. It supports high frame rates, 100, 120, and even fractional rates. Temporal sublayering is a feature which is added here to ensure backward compatibility mechanism for high frame rates. So decoders, so you can think that decoders which are like 50 FPS or 60 FPS, they have an ability where they can skip some frames and they can still interwork with this. And then we have temporal filtering. Temporal filtering is basically used to optimize the standard frame rate and high frame rate kind of pictures, especially when temporal sublayering is used. And it supports high dynamic range, both PQ and HLG, to basically cater to different kinds of brightnesses. And in addition to that, supports the metadata also for PQ. In addition, it supports the wide color gamut, and you can see, I mean, these standards are kind of already well known, the BT2100 and BT709. And I mean, these are, you can say some of these are kind of tick boxes. It supports YCBCR, ICTCP, full range coding. And the last one is kind of interesting, SLHDR1. SLHDR1 is a technology which kind of came from Technicolor. And what it allows the broadcaster to do is to deliver a signal which can be rendered both in SDR as well as HDR. So quite some innovations done to ensure, adaptability to legacy as well as new systems. Let's go to the audio's enhancements in audio, ATSC3 audio. So if you look at the enhancements, I would say there were basically two next-gen audio systems, which basically the ATSC3 proposes. One is to support MPEG-H and Dolby AC4. Now, these again came out of need from two different countries. MPEG-H is used in South Korea and Dolby AC4 is used in the US. Then ability to enable dialogue enhancement. Then user selectable audio tracks in alternate languages and video description services. Immersive sound. This is one of the very key features which ATSC3 enables. Is the fact is to enable the sensation that can, their sound can come from anywhere, and it gives the listener really a great experience even on a headphone. So a lot of new algorithms have gone into this, and then a good dynamic range control as well as improved coding efficiency. So if you look at the audio enhancements, so what ATSC3 has done is that it has used this object-based personalization ability, especially in the audio. And as a result of that, one of the key things which they have been able to do is to separate the music and the effects as a separate PID and the dialogue as a separate PID. Earlier, they used to go together, but there are enhancements in the standard by which they go separately. And this gives the ability of, because of the kind of the new generation audio decoders, now you can send through 4 complete presentations in 384 kbps, where earlier you were able to send only 2 of them. So significant amount of enhancements, especially in terms of personalization of audio, is what has gone into ATSC3. Advanced emergency information. So this is one of the very key features, if you think about it, because irrespective of the countries, natural disasters happen everywhere. And one of the key things you will notice is that whenever natural disasters happen, or even some kind of a tragedy happens, like fire being caught somewhere or some kind of an accident, always you will find that the usual broadband networks will be choked because people are using that for a lot of messaging, and they will not be able to, and they will be busy because they are handling so much traffic, especially in such kind of times when people are in a state of panic. So under such circumstances, one of the important things is how to make sure you reach out to the first responders and other people who don't have the broadband networks. And to enable that, ATSC 3.0 has introduced what is called as an advanced emergency information ability. And this is also enabled by Bootstrap. I'll kind of describe that in the next slide. But what it allows is geolocation targeted messages. It can tell where certain event has happened and also bring you the rich media which is associated with this. And earlier, if you recall, a lot of these contents were such that they would be like, they would crawl at the bottom of your screen. But then what this allows is the ability to update and say that, okay, I have seen the alert and I don't want to see the alert and things like that. So very advanced kinds of mechanisms are enabled in ATSC 3 for emergency alerting. So if we go to the next slide. So this is actually showing the physical layer aspects of how this is enabled, and there is something which is called as the wake-up function. And again, here the key thing is the bootstrap. Now let's recollect what we did about bootstrap. So bootstrap, as we know, is one of the is the initial discovery and entry point. We kind of looked at that, and the bootstrap has something which is called as the wake-up field, and which comprises of 2 bits. So what a receiver can do is that it can keep monitoring those 2 bits. It can keep looking at it and say, okay, there is nothing to worry, and suddenly it's, oh, some emergency has happened, and it wakes up. So there are 2 bits which kind of give 4 fields or 4 possibilities, and you can basically, the programmer can program. So one of them is no emergency, but then you can use the remaining 3 fields to make sure that there is a wake up event defined for the device, and also it is kind of designed to make sure that it doesn't act as a nuisance factor. You wake up only to an alert which you are interested in and not. So this is something which again is quite important, and one of the things to note is that it is kind of embedded as part of the framing structure, and obviously, there is one bootstrap available per RF band. So this is why this is significant from ATSC 3. Let's have a look at the security features. Look at security. So I didn't show this, but there is a studio to transmitter link, and this is kind of secured with encryption algorithms. And then receivers who receive the content from a broadcaster or transmitter have these signaling tables and applications which needs to be authorized, so they need some kind of a signing procedure to validate that the source of emission is really genuine and not something else. Content encryption, this is extremely important and quite, I would say, a very basic feature that is required for any broadcasting. So ATSC 3 supports that. It enables end-to-end protection of the content. And it's also important, especially when you're enabling a lot of services like subscription services and things like that, where the content is free, but then you still need the viewer to be registered, pretty much like the webinar that is happening now. There needs to be some kind of encryption, and this kind of enables things like pay-per-view and stuff like that. So security features are also built in. I just wanted to do a time check how much time I have. Okay. So since we are on the topic of 5G, I wanted to just highlight what is the synergy of this with 5G. One of the things, so let's go through this. So you can see that both ATSC 3 and OFDM have embraced OFDM. Both of them are IP based. Both of them actually use LDPC. LDPC is the forward error correction of choice in both of them. And then layer division multiplexing is one of the rudimentary forms of NOVA, which is used in ATSC 3. 5G has been thinking of NOVA. It is still not in the TS, but one of the recommendations is still there. Maybe someday it will pick it up. The other important thing is WCDMA assigned symbol rates. So this is one of the key things which ATSC 3 has done, is that it has made sure that the symbol rates are aligned to 384 kbps. And what it allows you to do is to embed frames of broadband within broadcast, and I will show that in the next slide, because you can be both time aligned and symbol aligned. Time alignment, this allows 5 millisecond increments, and this allows 10 millisecond increment or 1 millisecond increment for frames and subframes. I did not touch upon this, but ATSC 3.0 also enables carrier aggregation and channel bonding, which is also a feature of 5G. Cloud-based virtualized functions for both. This is more from the implementation on the network side. I mean, both 3.0, pretty much similar to 5G, has embraced virtualized core. And then cognitive RAN functionality. If you look at the way the bootstrap is, and think about the fact that it is an entry point to finding what the succeeding waveform is, you can think of some kind of a cognitive RAN functionality being embedded in 3.0. You know, the receiver first senses, or you can say it kind of smells, you know, is this waveform for me? Decodes the bootstrap, and once it finds it is for me, it will go ahead and decode. If it finds it is not for me, it will say skip and move ahead. So a lot of cognitive RAN functions are embedded, and similar kind of thought process has been there in 5G also with these techniques. And the last point is both of them are OTT compatible. So this is also one of the great synergies that and ATSC3 kind of already thought about it from what they have seen happening with 4G and other standards, that that is where the trend is going, that people are going towards more OTT kind of play. Next, I'll show the frame evolution. So this is an interesting concept. Basically, it shows that this is basically showing the same ATSC frame structure. You have a bootstrap, and then you have preamble, and then subframe boundary, and then the payload and subframe boundary. So what it is showing is that because you can have symbol aligned frames, this evolutionary frame can be something like an LTE frame or a 5G frame. And the bootstrap could be used to determine, or if you think of a converged receiver, the converged receiver can first decode the bootstrap to figure out whether this is LTE or 5G, or whether this is a broadcast frame, and similarly it can go ahead. And so ATSC 3.0 waveform designers already thought through these aspects and kind of made this more like a very flexible architecture in terms of framing, so that tomorrow, if somebody wants to embed a new kind of waveform within the frame structure, it's possible. So one can also think of embedding narrowband IoT frames, especially for sensors and things like that, which earlier again was not possible. So Bootstrap essentially gives that kind of an extensibility, which really makes it kind of, I would say, future proof. Going to the next slide. Okay, so this is actually showing the different standards of ATSC3. So ATSC 3.0 work is kind of still, I would say, most of it is done, and you can see that it consists of a suite of about 20 plus standards, which cover various aspects. The first three are kind of physical layer, and then you have the link layer, signaling, and then a lot of standardization with respect to what kind of services, how do you announce services, how do you report the services will be used, or how report the usage of them, and then how will you handle watermarks, both audio watermarks and video watermarks, how will you redistribute contents. See, one of the important things for broadcasters is that they redistribute the content to satellite as well as cable. So redistribution is also something which has to be thought through. Then application signaling, how do you do signaling in the user devices, companion devices, and then audio and video codecs, captions and subtitles, and then how there is also some work on interactive content and security, which I have not covered here because it needs more time. So essentially, it's a whole gamut of standards, and then each of them has a recommended practice which people have worked on, and that basically shows the kind of depth to which people have gone in to define the standard from all aspects. Okay, so now I wanted to touch a little bit on deployment. So we talked a lot about where it is used and how it is defined, the physical layer.
And in there, sir, it is very interesting, but I think we need to little bit bind up.
Yes. So I'll go through this. So I'll just go through this quickly. So the orange ones are basically showing the places where transmission has already started, and the light blue colors are the ones are the market areas where people have applied for FCC transmission, and the blue regions are the ones which are kind of the first market areas. And the other country which has embraced 3.0 is South Korea, and here also you can see that they are pretty much in an advanced stage. And it was already in an advanced stage because it was mainly triggered by their Winter Olympics in 2018. So you can see that the 4K UHD transmission was one of the key drivers for ATSC3, and now they are moving on to enabling more and more services. So this is kind of close to the last slide actually. And basically what we are saying is that it's a powerful new tool. It enables good opportunities of business. It has a flexible physical layer, huge improvements in picture and sound, also touches upon interactivity features, advanced emergency tools, accessibility, this I didn't touch upon, and then of course more robust signal and data capacity, and then the list goes on and on. So people can kind of read the standards and look at it. I mean, these are some of the references. So ATSC 3.0 looks like not a very good marketing number. So people have now started to call it as the next gen TV. And so I had a small video. Now I don't know, this did not play earlier. So I was thinking whether to give a try and see whether you guys can, I don't know whether you can look at it or not, but maybe I can unshare and play this. This was basically from the next gen guys. So let me stop sharing and try to share my media player and see if that can enable this or not. Okay, let me see if this, can I hear it? Can everybody hear it? Okay, I don't know if it can be heard on.
No, we are hearing only you. Yeah, I hope so.
Okay, maybe then I'll skip this. Let me open, close this. Let me try to share.
I think it should work.
Is this hearable or no?
Visual video.
Yeah, video and audio.
Audio, I don't know, maybe I'm not hearing.
Okay, fine. I think I will skip that. So basically, this is already in the next gen website already, which it is there. So essentially, it talks about the different services that are enabled. So I can keep it on mute and talk through it. So this is talking about FCC's approval, and it is talking about how within 6 megahertz from HD you could go to Ultra HD. It talks that it's a next generation platform. It is talking of watching live events with a lot of online things. It can deliver 4K UHD, it can give high dynamic range, has interactive features, multi-channel immersive audio. So what it says is it basically so it talks about robustness of this, it talks of SFN networks, and it talks of that fact that it can allow you to receive on mobile, in terms of devices, and it talks about alerting. It talks of audience measurement capabilities. So it can deliver to mobile devices, vehicles. So basically, it is telling that it is absolutely ubiquitous. So that's all. And it enables a lot of advertising kind of features also.
So
And
it's a
the additional thing
wonderful.
it mentions is that the standards are updated. That's all.
Okay.
Sorry, this video didn't work very
No,
well.
I was just saying that it's a wonderful presentation. As a closing remark, could you say a little bit against the 5G? Do you see them as adversaries or collaborators? How do you see ATSC 3.0? I think you had a synergy diagram, but could you make some comments how the two can work together, or are they adversaries?
Yeah, actually, they can work together, and we have kind of written some papers on that for the 5G World Forum as well. And what we feel is that there are a lot of places where this can, especially the idea of a converged network can enable a lot of things. If you think about it, broadcast has its strengths in terms of delivering a fat pipe, which is very high spectral efficiency, which is not possible sometimes in cellular world. So convergence definitely is one of the aspects in terms of 5G. We don't look at it as an adversary; we look at it as an enabler. So that's what I wanted to say. But then a lot of work is going on. My organization is doing a lot of work on that, and then more of that will come out later.
Oh, that's very great. No, from usual talk we had been listening always. This is a different standard, at least for me. It is new. So it is a great informative session. So thank you very much. And we have a couple of questions. So I think we should.
Sure.
Yeah, so I'll read some of them. There are a lot of, but I will read some of them. One of the question come in is, what carrier frequencies is ATSC 3.0 designed for?
So so right now it is designed for all the broadcast frequencies, and broadcast frequencies typically, if you look at different parts of the world, can be used in VHF, the higher VHF as well as the UHF spectrum. So typically, I would say 470 to 700 megahertz is what people think about. In US, I know that because of the FCC repack, the spectrum, the broadcast spectrum only is up to 608. But in Europe and all, it goes all the way up to 700. So essentially, it's basically the UHF spectrum where this is designed for.
Okay, very good. There is another which says, is ATSC 3.0 backward compatible with 1.0 version?
No, it is not designed to be backward compatible. That is one of the things which I touched upon in the first slide, in one of the first slides, that the people who designed this made sure it is not backward compatible. Mainly because of the disadvantages of ATSC 1.0, people don't, and see ATSC 3.0 reaps all the benefits of OFDM, which 1.0 didn't have. 1.0 was a single carrier 8 VSB system, and it was really difficult to handle things like echoes and reflections. We since we have designed it, we know it needs something like a very long equalizer to handle large echoes on the order of 100 or 90 microseconds. So in terms of the signal processing receiver complexity, it's ATSC 1.0 had a lot of pain points. Of course, it was an engineer's dream, but then in terms of getting it operational and all, it was not that beneficial. So 3.0, because it is OFDM based and reaps all the benefits. So that's why it was a conscious choice that this will not be backward compatible.
Okay. So there is another question. Is it possible to transmit different audio profile for mobile and different audio profile for broadcast?
Yes, it should be possible. The standard allows that.
Okay, fine. There is another question. How is the trial on 5G and ATC is picking up in India? Usually we would be late in picking up the new technology as compared to rest of the world.
Yeah, this is a bit of a tricky question. So I need to tell something because we are probably one of the organizations which is working in that area. We have broadcast receivers as well as low power, low tower transmitters in ATSC, radiating ATSC3. But this is mainly for some markets which are not in India, mainly in the US, where people have started doing trials. In India, right now, we are still waiting for some changes and doing some trials before it gets adopted. Some discussions are on. Yeah.
Okay. Can we use on-grid constellation allocation?
Yeah, that's an interesting point. So ATSC3 in some sense, actually, I think yesterday we had this talk on AI/ML. Actually, most of the constellation in ATSC3 are what they call as NUC, or non-uniform constellations. And the story behind that is that it seems like some of the study groups use some of the AI techniques actually in coming up with that. You have seen that particular slide. I mean, I can put that up again. Is how they optimize the BICM SNR and BICM curve, and a lot of that was achieved because they wanted this to be the best. Okay, I'm just going to that slide. Because they wanted this to be the best, they wanted to they optimized it to the hilt and found that only when you go to something like a non-uniform constellation. For example, if you can see my cursor, only if you go to a non-uniform constellation can you really achieve some of those very good BICM efficiency. So, so people use some of the AI/ML techniques actually to optimize this as an end-to-end thing as well. So that kind of thought process has gone in.
Okay, that's great. Is there any way we can carry the 5G contents on the ATSC 3.0 for short video clips as in WhatsApp, etc., as load sharing or?
Yes, definitely. I think this is a slide which I want to refer here. So this is what I mean, see, the ATSC frame structure actually allows you to carry any kind of frames, and if you can make it symbol aligned or time aligned, it definitely can be carried. So, and the bootstrap is one of the important or one of the powerful concepts which helps there, because the ability of the bootstrap to say that I want to receive the succeeding payload or to skip it enables somebody to do exactly what you say.
Okay, related to the same bootstrap, so one question is what is the major difference between preamble and bootstrap, and what should be the size of preamble and bootstrap? Is it fixed or variable?
Yeah, the standard actually talks of the specific sizes. I'll just go to this slide. The bootstrap, I think, typically, if I remember, it's probably maximum of 4 symbols. Now, the bootstrap usually is, as I said, an entry point. I mean, if somebody decodes a bootstrap and finds that the succeeding payload is not for me, he will skip. He will not even look at the preamble. But the preamble is something which is required to get the attributes of what kind of OFDM framing structure, OFDM attributes, which are used for generating the payload. So there is a significant difference between bootstrap and the preamble. So you can think of it as a linked list structure. I mean, there are some attributes here which are used to decode. Once you kind of pass the bootstrap, you decode L1 basic. Once you decode L1 basic, this gives a pointer to L1 detail. And L1 detail enables you to decode all these particular subframes. Hello.
One last question possibly, and I request participant they can drop me question. I link and we will try to give you back the answer.
Yeah, I can take
When
some
we
more.
talk of
We are not late.
When we talk of broadcast content for mobile devices, does the transmission take place through base station, which could also be combined with two-way voice plus data services, or do they have dedicated transmitters just like TV station?
I think as of today, the broadcasters are working on the same model as what it used to be, which is having their own infrastructure for transmission. But in future, with the convergence which is happening, it is possible that such kind of scenarios become a reality where, let's say, a broadcaster can, let's say, a broadcaster finds out that, hey, I have too much of spectrum and I'm not going to use all of it, and let's say I can opportunistically lease out a section of my spectrum to a telecom carrier, then such kind of business models are possible. So this is purely driven by the kind of business models, the kind of revenue sharing, and the kind of synergies. But yes, sometimes some of these can happen.
Okay. What is the desired injection level for the core level and enhanced level?
Yeah, I think this is detailed in the standard. I think if I remember, it goes all the way from probably 3 dB to 10 dB, and at a step of 0.5. But I think a lot of details are present in the physical layer standard, and I have an army of people who know this much better than I do, especially in the physical layer protocol.
Okay, okay. Usually equalizers are very compute intensive DS in receivers, especially in DVB-SC. What is the scenario like for ATSC 3.0 system?
So yeah, so that is one of the advantages of riding on an OFDM system, because OFDM system makes it very easy to do equalization, channel estimation, and equalization. So all usual methods which are applicable for ATSC3 for any OFDM system are what is used here also. One of the good things about I spoke about pilots. One of the good things about this system is that it has a rich set of pilots. I mean, you can see this pilot insertion block. So there are continual pilots, there are scattered pilots, there are edge pilots, which make sure. So a lot of these are kind of designed in a way so that it enables you to do a very good sampling of the channel. The other thing is the spacing between the carriers. That also is kind of optimized. There are some profiles which are optimal for mobile, for example, and some are optimized for fixed rooftop reception. So it's a pretty healthy mix of a lot of pilot. Actually, I would say it is the pilot patterns which help you in doing a very good and very easy channel estimation. Than what would be possible.
Oh, that's great. Maybe the last question. Can you write on how well ATSC and next gen TV complements or competes with MBMS from 3GPP?
I think that will need a lot of discussion. There is a lot of work which is done there, and a lot of work has been done in our organization also. We actually have a white paper or a study item in TSDSI which touches upon that, and I probably can share some of the references. There is also a group in Europe called 5G XCAS which has extensively looked at this. To say, one of the top, okay, I will probably list a few top items, in terms of EMBMS and ATSC3. So EMBMS, in some sense, is what has been found. I think the top things is the fact that EMBMS has the limitation of a short frame duration, whereas ATSC3 or broadcast waveforms don't have. And the kind of time interleaver and frequency interleaver, you can see in the diagram that 3.0 can enable. That flexibility is not there with EMEMS. So one of the places where ATSC3 scores very well over EMEMS is in terms of mobility. It's a very good Doppler performance. The other benefit which you can see, and a lot of people have also compared, discussed and all, is the robust bootstrap. So if you look at the bootstrap works, as I said, minus 6 dB. In EMEMS, you have something like a common axis subframe, which is a little bit inferior, but then that also does the job. So so there are multiple things like this, and I mean I just gave two differences which came top of my mind. The other thing is, I would say the other important things are in terms of the ability to handle what do you call it as ability to handle single frequency networks. That is also one of the key important things. EMBMS does have some benefits, but not a whole lot as ATSC has. One of the things which I did not touch upon in ATSC3, which also has been there in one of the documents, is the ability to give a lot of densification, which also the previous standards did not allow. So EMBMS versus this is a long thing. Also, if you look at the kind of FECs which are used, EMBMS uses turbo. This uses LDPC. LDPC is marginally, I would say, superior than EMBMS. In terms of spectral efficiency, ATSC3 is also better. But then if you want to normalize and look at it with a fair point, you will see that yes, ATSC3.0 is somewhat optimized more for a terrestrial reception, and EMEMS is more for mobile reception. So the constraint points are very different between both of them. So
okay. I think it is understood. Thank you very much for this great talk and great information. Huge a lot of information we got it from this new sort of topic. Thank you very much, and I would request audience and participants, please be there tomorrow as well. So tomorrow again we have at the same time very important and very good talk, that is a 5G system aspect or perspective system design, and that will be delivered by Director Tushar from Samsung. So don't miss and join tomorrow again at the same time, 7:30. Subhash sir, are you there? You wanted something? Actually, I could not send a message. So if you are there, if you have something, you can put it. Wanted a feedback sort of. If not, so thank you very much. Thank you all participants.
Thank you everyone
Comsoc leader
for giving me an opportunity.
Thank you very much. Thanks a lot. Dr. Alok, thank you. I was a little late. Sorry for that.
Yes. No, that's great. Thank you.
Yeah. Okay. Thank you all of you. Good night. See you tomorrow.
Thank you. Bye.